Right. This is the 10th lecture in our course, and we're going to be continuing on with acid-base equilibria in this lecture. Right. Specifically, we're going to be covering material from sections 4, 5, and 6 of chapter 18. Let's remind ourselves the approach we take when we solve an acid-base equilibria problem. We mentioned this at the end of last lecture. Okay, first, write down the balanced equation, then you can derive the expression for Ka, then you define X as the change in concentration that's occurring during this acid-base reaction. You construct your reaction table, your ice table in terms of X. You make the simplifying assumptions, and you substitute those values in for Ka, and you can solve for X. So let's right off the bat start a practice problem. The practice problem we did last class, at the end of last lecture, was one where we did not know Ka. All right, we had a pH, and from that we could find X, the unknown concentration, and then we could substitute that into our expression for Ka and solve for Ka. This question's a little bit different. Maybe a little bit more typical in what you would see in this part of the class, where you will know the Ka value. You can look the Ka value up for your particular acid, and then you have to determine, okay, if you have a certain concentration of your acid, what is that H plus concentration going to be based on the Ka value, and why do you care about that? Well, then you can use that H plus or hydronium ion concentration to determine a pH. Okay, so you're really doing this to determine a pH for a weak acid solution based on a known Ka value. Okay, so in this question we have propanoic acid, which has this chemical formula, and really it's just again the COOH is the acid. That's what tells us it's a weak carboxylic acid. We can simplify it as HPR. Propanoic is PR, that's the abbreviation, and H tells us it's an acid. That's the proton it loses. Okay. It's used specifically to keep mold from growing in food, in case you're interested. Okay. We're looking for the hydronium ion concentration of a 0.1 molar solution of this acid, and the Ka value is given here. Okay, so how do we do that? Well, we follow that roadmap. Okay, so we're going to first have to write our balanced chemical equation. So propanoic acid plus H2O. Okay, those react, it's acid-base. So we get the conjugate base plus H3O plus. Okay. So we also know our Ka value. We can write an expression for Ka, and it's going to look very similar for any weak acid, right? It's just going to be your hydronium ion concentration plus your multiplied by your conjugate base divided by your concentration of your weak acid to start with. Okay. And we know that this equals 1.3 times 10 to the negative 5. Okay. So now we can construct our ice table. Initial concentration, change in concentration, and equilibrium concentration for all of our components. So initially we had 0.1 molar of our acid. Okay, water we don't have to consider because it's a bulk solution, and we don't have any of our products to start. Okay, the change is going to be minus X. For our weak acids, some of it's going to dissociate, and the amount that dissociates will be an increasing amount of our conjugate acids and bases. Okay. so then at equilibrium, right, would be 0.1 minus x, but remember we're not going to consider that because we're going to assume that the amount it dissociates is very small, so we're just going to keep that as the starting value. And then at equilibrium, these just become x, right? 0 plus x is x. Okay, so now we can solve for our Ka. So our Ka, if we go back up here and plug these in, that's just going to be x squared over 0.1 at equilibrium. Right, so we can solve for this. So if we go down here, x squared over 0.1 equals 1.3 times 10 to the minus 5. So we can multiply through both sides by 0.1. So 1.3 times 10 to the minus 5 times 0.1. You can take the square root of both sides. Right, and then we can find x is 0.00114. Okay. So that means that would be the concentration of both our conjugate base, PR minus, and our conjugate acid, H3O+. The one we're really concerned with usually is the H3O+, because that's what's going to give us a pH. Right, so H3O+ concentration would be 1.14 times 10 to the minus 3 molar. Right, and if we wanted to, we could just take the negative log of that and calculate a pH. So if we look at the percentage of an acid that's dissociated, right, you could take the amount that gets dissociated, and that would be our x value in the previous problem, divided by the initial concentration, multiply that by 100, and that would tell you the percent dissociated. So as the initial concentration of decreases of the acid, the percent dissociation will increase. A decrease in the concentration of the initial acid would mean a decrease in the concentration of the dissociated acid, which would cause a shift towards the products. The fraction of ions present increases even though the actual concentration of the dissociated acid is decreasing. So that's one thing that's maybe kind of hard to wrap your brain around. So let's try a practice problem. 2011 researchers showed that hypochlorous acid, HClO, generated by white blood cells kills bacteria. So now we have to calculate the percent dissociation of two concentrations of hypochlorous acid, one at 0.4 molar and the other at 0.035 molar. And the Ka value for hypochlorous acid is given here, right? And remember, the percent dissociated is given by this equation. Okay, so now we can set this up the same way we did before. Basic steps are going to be the same. Okay, just remind ourselves, what is our reaction? We have hypochlorous acid, HClO, plus water, and it's in equilibrium with its conjugate base plus H3O+. Okay, and the Ka value is given at 2.9 times 10 to the minus 8. And I always like to just write the Ka expression right away, even though it's the same every time. Okay, there's our Ka expression. Now we can set up our reaction tables, and we're going to have two separate reaction tables. And what I can do, I'll just show them in different colors. So the first case will show in red. So red will be the first condition, part A, where we have a 0.4 molar starting concentration. So our initial here for hypochlorous acid is 0.4 molar. H2O again, don't need to consider that one. And we have zeros for both of those. The change, again, we're going to be minus X. We're going to lose some because it'll dissociate. And that will mean we gain the equal amount of both of these products because it's 1-to-1 ratios of both. And we have at equilibrium, right? We don't consider that change for the acid, and we just have X's, okay? So in a question like this, you might not need to really write down this table, but I think it's good just to get in the practice of it till you get comfortable with it. They tend to be the same thing over and over again for these types of problems. We will move on to more complex problems that will get a little bit more difficult, that you'll really need to keep track of these more carefully. Okay, so the second condition, we'll just show that in blue on the same sort of table here. We had 0.035, right? We still have minus X, but again, at equilibrium, we're just assuming that nothing changes too much. And we have the same values over here for that condition. Okay. Now, if we want to actually solve for X, let's do that. Let's do that for the red condition first. So we plug those values into our Ka expression. So here we would have X squared over 0.4 is equal to 2.9 times 10 to the minus 8. Right, when you solve for that, X is going to be 1.08 times 10 to the minus 4. And if we wanted to find the percent that was dissociated, it's just going to be the amount that's dissociated, which would be X, 1.08 times 10 to the minus 4 molar, divided by the starting concentration, which would be 0.4 molar. So we get something like 0.00027, which if you multiply by 100 would be 0.027%. Okay. So now let's compare that to second condition B, where we have 0.035 molar to start. So if we plug those values into the Ka expression, right, we're still going to have X as our fraction or amount that has been dissociated. And it still equals that same Ka value, 2.9 times 10 to the minus 8. When you solve for X here, you get 3.19 times 10 to the minus 5. Right, and then finding the percentage that's dissociated, right, that'd be 3.19 times 10 to the minus 5. And you can see that's a smaller number, right? If we compare that number to this number, it's a smaller number. Divided by our starting concentration times 100. So that would be 0.0911%. And you'll notice the absolute concentration of this is smaller, but the fraction that's dissociated is actually larger. So the more dilute that acid is, the higher the fraction it will dissociate. And that's kind of what that was being explained on that previous slide. Things get a little bit more complicated. And one of the ways that they can get complicated is with polyprotic acids, and those are acids that have more than one proton. We've mentioned some of these before in this class, like sulfuric acid, H2SO4, and phosphoric acid, H3PO4. So sulfuric acid is technically a strong acid and completely dissociates. So you don't have to consider its equilibrium, but something like phosphoric acid, that's a weak acid, will have partial dissociation, and it has 3 protons, so it gets fairly complicated. So we can look at this first dissociation. So if we have H3PO4, the first proton it loses, it becomes H2PO4 minus. Okay, and that has a particular Ka value here shown as 7.2 times 10 to the third. We can write that Ka expression for that first proton it loses. Well, the conjugate base of that reaction becomes the starting point or the acid for the next proton that gets lost. So now we have H2PO4 minus losing a proton and becoming HPO4 2 minus, right? And so that particular proton being lost or donated has its own Ka value. And here it's written as 6.3 times 10 to the 8th. Notice how it's smaller. That second proton is always going to be smaller than the first proton's Ka value, right? Because the first one that gets lost first is going to be a stronger acid because it happens first. So it's going to have a smaller larger Ka value. Right? So the smaller Ka value would be the next one. Okay. And then this has another proton, right? Still has a proton left. That can be lost. So that becomes the acid in the next step, and it loses a proton and becomes PO4 3 minus. Right, and then the Ka value for that is shown here. So you can write Ka expressions for all of these. Right. And then handling a problem like this, if you're talking about how much H3O plus is produced because you want to find a pH, usually you can neglect the amount that's formed from any step after the first step. You can kind of neglect that because the amount that's formed here in the first step is going to be so much larger than the next steps. Here's just a table of some successive Ka values for some polyprotic acids. So oxalic acid, sulfurous acid, so it's like sulfuric acid, but it's SO3 instead of SO4. And that makes it a weak acid. You have phosphoric acid that we shown on the previous slide, arsenic acid, carbonic acid, and hydrosulfuric acid, H2S. You'll notice that the Ka2s are all lower, and quite a bit lower actually, than Ka1s. And then Ka3 even lower still. Okay, so let's try a practice question using a polyprotic acid. And this one will be ascorbic acid, which has 2 protons that it can give up, and we can abbreviate that as H2ASC. All right, this is vitamin C. Okay, it's a diprotic acid with Ka values of 1 times 10 to the minus 5 and 5 times 10 to the minus 12. All right, it's naturally found in citrus fruit. Okay, so we're going to have to, in this problem, calculate our first step's conjugate base and the second step's conjugate base and the pH of a 0.05 molar solution of this acid. So you can kind of read the plan that we're going to undertake here. Basically, it involves two subsequent steps of what we've just been doing for our roadmap for these types of problems. Okay, so we can first write our color do I have? There we go. We can write our first proton. So that's H2 ascorbic plus H2O, and it goes to HASC minus plus H3O plus. Okay, and our Ka for that, Ka1 we'll call it, is 1.0 times 10 to the minus 5. And that expression is H3O plus times our conjugate base divided by our starting concentration of that acid, H2ASC. Okay, so we have our expression for Ka. Now we can set up our reaction table. So our reaction table and initial change equilibrium. Our initial concentration we were given as 0.05, and these are zeros. Change minus x, even though we don't really consider it, plus x and plus x. So at equilibrium, we can just assume this is basically what we started with, and these will both be x. So we plug those into our expression for Ka. Ka1 equals x squared over 0.05, and that equals 1.0 times 10 to the minus 5. So we solve for x, and we find that x is 7.1 times 10 to the minus 4. Okay. Right, so if that's x, right, x is our H3O plus concentration. So we can calculate the pH based on that. So if it's 7 point, I think technically it was 7.07. I just rounded it to 7.1, but let's keep that unrounded. Okay, if that's what the H plus concentration was, the pH is the negative log of that. Which would be 3.15. Okay, so we could calculate the pH there. Right? And again, we assume that all the H plus is coming from that first proton. And all the subsequent step was going to be negligible. So that's why we can use that value to calculate pH, even though we know there's another step, another proton to lose. Okay, so that is the pH. X is also going to be the concentration at equilibrium, at least of this first step, of that HASC minus. Okay, and that's what we're going to use for our starting concentration in our next equilibrium step. So our next step, and I'll do this in a different color. Let's do it in blue. Right, our second step here is going to be HASC minus plus H2O in equilibrium with ASC2 minus plus H3O plus. And we're given a Ka for that, so we can write the expression Ka2 equals ASC2 minus times H3O plus divided by HASC minus. Okay. And that equals 5 times 10 to the minus 12. Okay, now we can set up our reaction table. For this, so our initial concentration, again, is going to be 7.1 times 10 to the minus 4 molar. And where we're getting that from the first step. Okay, that X value we calculated in the first step was the equilibrium concentration of that. Okay. H2O, again, we ignore that, and we can again assume that these products' starting values are 0. Right, so changes, minus X plus X plus X. And again, don't consider that minus X here, so that just stays the same. These are X's. So now we can plug those in to our expression for Ka. And I did a little bit of a mistake here. For H3O plus, we're not really starting at 0, right? Because this first step, we calculated that. Right? That was the same value, X, right? These are both X. So we're actually starting with some. So that was 7.1 times 10 to the minus 4. So we're assuming, and we're, to make it easier on ourselves here, we're kind of ignoring the additional amount of H3O plus that would be produced here. So we're just kind of assuming those are negligible. So that's going to be our value for H3O plus. So now we only have one X to deal with in our Ka expression, which makes the math quite a bit easier. Okay, so we have X for the ASC2 minus concentration times 7.1 times 10 to the minus 4 molar for H3O plus divided by our starting concentration, which again is 7.1 times 10 to the minus 4 molar. Those are both in molar. And that equals 5 times 10 to the minus 12. Well, you can see here that X, the 7.1 times 10 to the minus 4 will cancel. X is just going to be equal to 5 times 10 to the minus 12. Right, so that's pretty easy. If the value is on a problem like this, in any case, is going to be the same as the Ka value, that concentration of your your conjugate base there. Okay. So that's an example of how we can use two of these types of equilibrium problems in succession. If we think about acid strength of non-metal hydrides, the strength is going to depend on the electronegativity of the central metal, non-metal element, and the strength of that non-metal to hydrogen bond. And if you think back to the first quarter of this class in the periodic trends, right? How do the trends for this property, how would it change when you look across a period or down a group? Well, as you go across a period, acid strength will increase. Okay? And that's because electronegativity is increasing across a period. So as you go from left to right across a row or a period in a periodic table, your elements are going to be getting more electronegative, right? So the acidity would therefore increase. And that's because the more electronegative the element, it's going to pull more of the electron density away from the hydrogen, which makes it more like a proton and easier to give up. Okay, as you go down a group, the acid strength is also going to increase. And that's because the length of the bond between that non-metal and the hydrogen is going to increase down a group, and therefore its bond strength decreases. So the more electronegative that element is, the more acidic it will be, and the weaker the bond, so this is the weaker the bond, the stronger the acid. Because the easier it is to give that up. And as we can see, if you look at some of these examples, if we're going across or down a group, probably the easiest one to see is down a group. From HF to HCl, right, we're going from a weak acid to a strong acid, and actually these subsequent HBr and HI acids are stronger still. Kind of hard to compare though, because they're all strong, right? They all fully dissociate in water. All right, if we look at the oxygen group now, H2O is really not an acid. We've seen it can be both, but it doesn't really, not really considered an acid by any means. But if we look at H2S now, one step down in that group, its Ka value is shown here, 9 times 10 to the minus 8th. Go down one more step, and you see there's a pretty big jump there in the Ka value. So we're getting stronger as we go down that group. So those are the non-metal hydrides. If we look at oxoacids, oxoacids have acidic H bonded to an oxygen atom. Okay, and the strength of oxoacids depends on the electronegativity of the center non-metal, right, just as before, and the number of oxygen atoms around that center element. Okay, so for oxoacids that have the same number of oxygens, the acid strength increases as the electronegativity of that other non-metal increases. For oxoacids with different numbers of oxygen atoms, the acid strength increases with the number of oxygen atoms. Okay, so the stronger oxoacids will have more oxygens, and they'll have a more electronegative non-metal bonded to those oxygens. Right, so if we look at some examples of these, part A here you see examples where you have the oxygen bonded to a halogen. So as electronegativity increases, and they all only have one oxygen. So as the electronegativity increases here, from iodine to bromine to chlorine, right, as we go up that column towards the top, you can see that the difference in these deltas gets bigger, which means there's more electronegativity, electron density being pulled here by the more electronegative chlorine, which makes this more like a proton and easier to lose and more acidic. Right? And then comparing, a chlorine with one oxygen, oxoacid, or a chlorine with 4 oxygens, right? There's just more, that's a much bigger change or difference in the electronegativities there between the hydrogen and the oxygen. With this number of oxygens, there's just so much more electronegativity and ability to pull electron density away. Okay, we don't really talk too much about oxoacids in the class, but if you have to determine which one's stronger, right, look first at the number of oxygens and then at the center atom and see which one is more electronegative. Right. We can also have hydrated metal ions that are acids. So some of them, they're acids because they can transfer a proton, and thus they can form acidic solutions. So if you look at your metal ion in solution, that's just, generic metal, M with the N plus charge on it. When you put that in water, it can actually be hydrated by water. Water will coordinate it. Okay? And if it's small, if the metal's small and highly charged enough, it will draw enough electron density away from the OH bonds in those water molecules to actually have one of them release a proton. Right, so here, it's going to draw enough electron density away from one of the oxygen or one of the waters to where one of them will give up a proton to water to make H3O plus, and then you'll have an OH minus connected to that at one spot, coordinating that metal. Right, and it's probably easier to see this graphically or in form of a picture, right? Aluminum here has a +3 charge. It's going to be coordinated by 6 water molecules in solution. It has enough charge on it, density, that it can pull electron density away from waters and such that a nearby water molecule can pick off hydrogen from that. And then you have an overall case where you have 5 waters now coordinated in aluminum plus an OH group and then 1 H3O plus. So thus it's acting like an acid. It's donating a proton. This big aluminum water complex can donate the proton. Okay. So let's switch our focus now and focus on weak bases. So a Bronsted-Lowry base is a species that accepts a hydrogen. So in our case here, we can write a generic equation here as B standing for base plus water goes to BH plus OH minus. So that base is taking a proton from water. Right? And we can write a base dissociation constant Kb. It'd be our conjugate acid times OH minus divided by our starting base concentration. And in this definition, none of the Bronsted-Lowry bases actually dissociate in solution, but the ions are produced when the base reacts with H2O. Here's just a table of some Kb and pKb values. You'll notice that, as the Kb, if the Kb is higher, that means it's a stronger base. Okay, so as the Kb gets lower, you'll notice that the pKb gets higher. So that's another good thing to mention. pKa values and pKb values have the sort of inverse relationship in terms of acid and base strengths. So Kb or Ka, the higher that value is, the stronger that acid or base is. pKa or pKb, it's the opposite. The lower the pKa or pKb values, the stronger the acid or base. Okay, let's try an equilibrium problem with a base. So dimethylamine is CH3. Those are methyl groups. There are two of them. And the amine part is the NH. Okay. It's a key intermediate in detergent manufacture. It has a Kb of 5.9 times 10 to the minus 4. What is the pH of 1.5 molar dimethylamine? Okay, so our particular plan is here. What we're going to have to do here, because this is a base, we're going to have to solve an equilibrium problem and get a concentration of OH minus, and then we'll use our relationship between OH minus and H plus to convert and calculate an actual pH. So first step, as always, write down our equation, chemical reaction. So dimethylamine, CH3,2NH plus H2O. Now we're being told it's acting like a base, right? So what do Bronsted-Lowry bases do? They take protons. Sorry, it's 2, so we can do NH2. And it's a plus charge because it's adding H plus. And we have an OH minus. So our Kb value is 5.9 times 10 to the minus 4. And we can write this Kb expression. Kb equals our conjugate acid times our OH minus concentration. Sorry, that's supposed to be a bracket there. Divided by our starting concentration of dimethylamine. Okay. And we're also being told that our starting concentration is 1.5 molar. So we can set up our reaction table. So our initial concentration is 1.5 molar. And 0 and 0. And we lose some of that. We're going to gain. We're still assuming that the amount dissociating or grabbing a proton, that's not going to change very much relative. Okay. And sorry, these should be plus x's. So now we can plug in for Kb, our expression, right? It's just like Ka, we're going to get x squared over our starting concentration, but now it's the starting concentration of our base, so that's 1.5, and that equals 5.9 times 10 to the minus 4. So we can solve for that, and when we do, x is going to be 0.0297 molar. Right, so this is our concentration of OH minus. It's also our concentration of our conjugate acid, but we don't really care so much about that. We care about our OH minus. Right, so we can use POH. That's going to be the negative log of OH minus concentration. So the negative log of 0.0297, which is 1.52. Okay, we're still not done because the question's asking for pH, not pOH. So remember that relationship, pH plus pOH equals 14. So pH is just going to be 14 minus pOH, or 14 minus 1.52. And that is 12.48. Okay, does that make sense? Well, yeah, it's a number that's bigger than 7, so it's a basic solution, which it should be because we're talking about dissolving a base in water in the absence of any acid, so the solution should be basic. Okay. You could also, just to remind ourselves, X is equal to OH minus. And why did I write it as HO? Sorry, this should be OH minus, not HO. That might have been confusing. But just to remind ourselves, when we're solving for X, right, X is OH minus concentration. And so that's what we're using to plug in to find our pOH. Okay, you can do this the other way, right? You could use OH minus concentration and use KW to get H plus concentration. And then from that, calculate a pH, but I kind of prefer to do it this way. So if we look at the anions of weak acids, they often function as weak bases. So if we have a acid here that has already lost its proton, that anion would just be A minus. So we're just calling this acid a generic term, A. So the generic formula would be HA. It loses that proton and it becomes A minus. And remember, we called that a conjugate base. And why did we call it that? Well, because if we go in the reverse direction, it can actually pick up a proton. So in this slide, we're kind of showing this, the typical reaction of HA going to A minus in reverse, right? So we have A minus now, it can react with water and go back to HA, which in turn creates OH minus. Okay, so that's what we mean by saying that these anions of weak acids can function as weak bases as well. Okay, so if you have a solution of HA, it's acidic. If you had a solution of just A minus by itself, that would actually be basic. So even if you, let's use ascorbic acid as an example, because we've used that in a couple practice problem, a couple practice problems ago, right? So that is we call it ascorbic acid. But what if it has lost all of its protons? Then it becomes ascorbate, and it actually would, without any other ascorbic acid form of it around, if you put just ascorbate in solution, it would act like a base. The other example here is we have HF, right? HF is a weak acid and can partly dissociate into F minus in solution. HF is a weak acid. It's much weaker of an acid than H3O plus is. So this equilibrium actually lies to the left, right? So HF concentration is much, much greater than the F minus concentration. But OH3 plus from the HF is going to be greater than OH minus solution. Therefore, the solution itself is acidic. What if we, instead of HF, we used NaF? Okay, we dissolved NaF in water. it dissolves completely because it's a strong electrolyte. And F minus then, without having the hydrogen on it, is acting now like a base. So in solution, F minus can pick up a proton from water, make HF, and then it produces OH minus. Okay, so if we think about, equilibrium favoring the formation of weaker acid and weaker base, since HF is a weak acid, is a stronger acid than H2O, right? This equilibrium also lies to the left, right? So the equilibrium is going to lie towards this direction. And much like the previous example, the OH minus from this reaction is actually going to be greater than the H3O plus from H2O. So this actually becomes a basic solution. And here's a neat kind of trick you can do with the Ka and Kb expressions. So you can write a dissociation, an acid dissociation, and a base dissociation for the same the same weak acid, let's call it. And remember from equilibrium that the equilibrium constant for the overall net reaction that we see here, right, is going to be K1 times K2. So our acid Ka expression here is H3O plus times A minus divided by HA. And our Kb for the second equation is HA times OH minus over A minus. So when we multiply those together, right, you can see that A minus and HAs are going to cancel. What we get is H3O plus times OH minus, which should look familiar, right? That's just the definition of Kw. So that relationship is true for any conjugate acid-base pair. Okay, let's try another sample problem. Sodium acetate here. So that's very similar to acetic acid, but now the proton is being replaced by a sodium. So this is going to act like a base in solution. It's used in textile dyeing. What is the pH of 0.25 molar sodium acetate at 25 degrees Celsius? We don't really care about the temperature in this problem. The Ka of acetic acid is 1.8 times 10 to the minus 5. Okay, so what they're doing here is they're giving us the base form, the acetate form of this. We're trying to determine the concentration of it and of subsequently of the H plus concentration to determine the pH. But they're giving us the Ka value of acetic acid. So what we're going to have to do is convert that Ka into a Kb and then determine the OH minus concentration. So our equation here, right, if we put sodium acetate in solution, it is a strong electrolyte. And what are we going to get out? We're going to get sodium ions and the acetate anion. Okay, and remember, I'm just abbreviating acetate AC as CH3COO minus. It's just easier to write AC minus, but just to remember that's what we're talking about. So the equilibrium this is going to undertake in solution is going to be based on the AC minus. And remember, that is a conjugate base from acetic acid, so it's going to act like a base when it's by itself. So we're going to get H HAC plus OH minus when it pulls that proton off of H2O. Okay. Now we can set up our reaction table. So we're starting with 0.25 molar acetate. Water, don't care about. We're not starting with any of that. So this, again, minus X plus X plus X. Again, we're assuming that the amount lost of our acetate is negligible, so that stays 0.25 molar. And these would both be X. Okay, so now we can write our expression for Kb. Kb would be our OH minus concentration times HAC divided by AC minus. Right. And we could, plug those values in. The problem is we don't know Kb. Okay, so we'd have two variables, no way to really solve for that. What we're given, though, we were given a Ka, and that is 1.8 times 10 to the minus 5. Right, and we just mentioned that, Ka times Kb equals Kw. So we can solve this for Kb. So Kb is just going to be Kw over Ka. So that is 1 times 10 to the minus 14 divided by 1.8 times 10 to the minus 5, which is 5.56 times 10 to the minus 10. Okay, so now we have something we can set this equal to. Okay, so we can plug in our expression, equilibrium concentrations for Kb. So OH minus is going to be X, HAC is going to be X, so that'd be X squared over 0.025, and that equals 5.56 times 10 to the minus 10. So do the math there, and X is going to be 1.18 times 10 to the minus 5 molar. Right, so what is X? Well, X is going to be the concentration of HAC. It's also the concentration, more importantly, of OH minus in this equilibrium. So using that, we can calculate the POH. So POH is going to be the negative log of OH, which is 1.18 times 10 to the minus 5. So that gives us a POH value of 4.93. And converting that to a pH, pH plus POH is 14. So if we do 14 minus POH, we get 9.07. Okay, so our pH here is 9.07. Does that make sense? Well, yeah, because we're adding a ascorbate, which is acting like a base, so the pH should be greater than 7.